Swayam Prabha. Digital India. Educated India.
Welcome to the last chapter on Point-Set-Topology course, part 1. So this will be topological groups and topological vector spaces. The interaction of algebraic operations, of addition, scalar multiplication, etc. with the Euclidean topology on the one hand, and the important example that we had, Banach spaces, right? They are very important. Okay, what are the Banach? One Banach space we emphasize, namely the set of all bounded functions on a given set, right? So all these things together motivate the study of the so-called topological groups on the one hand and topological vector spaces on the other. Okay, so this last chapter is devoted to a brief introduction to these two concepts. The first section is just a brief introduction to topological groups, and the next section we will take up topological vector spaces. Okay, it is no way claimed that this is exhaustive or comprehensive. This is just a brief introduction. Okay, let me start with recalling the definition of what is a group first, so that I can use those notations comfortably. I assume that you know already groups because we have even studied group actions, right? So a little bit of group theory, whatever groups, homomorphisms, subgroups, etc. I suppose you know, but let me recall them first for ready reference also. First of all, you may treat a group as an ordered triple of a set G and a binary operation mu and a distinguished element E, where G is a set, mu is G cross G to G, that is the meaning of binary operation, which is associative. For a short notation, we will use mu of G comma H as G composite H. So G and H are elements of G. G circ H is also inside G. You may read it as G composite H or G circ H. Axiom of identity. There is one axiom, which means another condition here is that this distinguished element is called identity. Why? Because its action on other elements, E composite G is G, and on the right side of the G composite E is also G for every G. Okay, so it is acting identically on other elements. That is why. The third axiom is that for every G in G, there exists a unique element G inverse. Okay, G to the minus 1, we read it as G inverse, such that what is the property? G composite G inverse equal to G inverse composite G is the identity. Okay, the element is called the identity element, which I have been referring to. For every G in G, the element G inverse is called actually inverse of G. We will also use the short expression G is a group. just like we say X is a topological space. So we can say just a G is a group instead of writing the triple G, mu, E, etc. each time. Often, even the simple notation is composite. Instead of mu of GH, we are writing G circ H. But most often, when there are no other compositions, we will just write it as GH. If there are 2, 3 compositions, then we have to distinguish. You can't write all of them as GH. Okay. Even there are two different groups. Okay. One is a domain and another codomain. We are using the same GH here and G prime H prime there to mean that we have to take the corresponding multiplications from G and G prime respectively. So such short short notations or abuse of notation, which is there in the practice by stalwarts, all the way goes back to Euler and so on. We can't change that, so we better follow those rules. In a group G, if the composition happens to have this property, namely G composite H equal to H composite G for all G and H, then G is called an abelian rope or a commutative rope. Okay, this is similar to the case of integers, rational numbers, real numbers, and so on. So there, the standard notation is plus, G plus, right? G plus to G composite H. But that is not forced on us because there may be more than one composition, both of them commutative. Okay. So then you have to choose which one is plus and plus prime and so on. So that is also not, it is only customary. Therefore, you have to follow the customs here rather than rigid rules. Rigid rules will be followed, logically in our mind. That much we have to do. By abuse of notations, it just means that you are not going to get confused by this notation. That is the whole idea. Okay. Let G be a group together with a topology on the underlying set G such that the product map, namely x comma y going to x y inverse, that I am going to denote by nu for a while, that must be continuous. Okay. What is the continuity here? G is a topological group, it means it has topology. Okay. So it's a multiplication is here. Then condition is that this multiplication is continuous, means what? Here there is a topology. Here I have to take the product topology. Okay. The product topology from given topology on both G and G here. That's what I have to take. Under that, this must be continuous. Okay. We then call G is a topological group. A subgroup H of G together with the subspace topology will be called a topological subgroup, provided what you have to do, the group operation is also the same because it's a subgroup. Okay. So however, when the context is clear, we may simply mention this as a subgroup. Likewise, homomorphisms from G to H between topological groups, okay, are always assumed to be continuous unless mentioned otherwise. Okay. Precomposing the continuous function mu from G cross G to G by y going to E comma y. See, y going to E comma y is a is a continuous function from G to G cross G, right? It's like a coordinate inclusion. Followed by xy going to xy inverse, E becomes x. So this x becomes E, sorry. So this becomes just y going to y inverse. So that map I am denoting by eta y, it's called the inversion map. Eta y is y inverse, because y inverse is uniquely defined, okay? This map is called what? Inversion map. It is called it becomes continuous by this observation. There is no, I am not making this as a hypothesis now. This is a follow. This is a consequence, because it's a composite of these two functions. Likewise, if you take xy going to, see, first composite is nu and then take eta. So xy going to xy inverse is what? Identity comma eta, right? Therefore, this is also continuous. Now composite with xy inverse, that will become xy going to xy. The nu of x comma y inverse is x, y inverse, right? So that's equal to xy. So this is actually the multiplication map mu, which we started with. That will be also continuous. So in one single go, by taking this definition, namely xy going to xy inverse, we have made taking inverse of an element, also taking x going to xy. Both of them are continuous. Okay. Once you have both of them continuous, you can recover the continuity of mu g inverse, continuous nu, that means xy going to xy inverse also. So they are equivalent. Instead of one definition, you may have two different conditions. Combined with that one, it will give you the first condition. So they are equivalent. Okay, so 32 and 33 together imply continuity of muons. All right. So here are some examples now. Any group together with the discrete topology or indiscrete topology is a topological group. See, you have already a group, so group operation you don't have to change. You put a topology, we are very familiar with putting lots of different topologies, right? You put a topology, discrete topology, cross discrete topology is discrete, the codomain is discrete, but any function from a discrete topology to any other space is always what? Continuous. Similarly, indiscrete to indiscrete, any function into an indiscrete space is also continuous. So out of this, discrete topology is not so disinteresting. We have already done one of them, namely action of a discrete group on a set and so on. But the latter is, namely indiscrete topology, is most disinteresting one. We will never have an occasion to use that one. Okay, but what may trigger some thought process here is that these two extremities are there, right? They are both topological groups without changing a group. So you may think that topological groups, after all, have no special properties at all. The topology for a topological group may not have no extra properties at all. If at all there are properties, it must be because of the group theory, you may see. Wait a minute, that is not the case. So we are going to prove something out of this. Maybe you may think it's nothing. Okay. So not all topologies on a topological group, even if you change the group structure, maybe will be topological groups. So we will see such things. So that being the abstract part, let us come back to some reality, namely genuine and useful examples. The real numbers, complex numbers, these were the motivating examples for us for this abstract definition, right? Along with standard addition and standard, if you take a non-zero complex number, there is multiplication also. They are all topological groups, right? The complex numbers of unit length, they form a closed subgroup of the respective multiplication topological groups, complex or real numbers. Okay, if you take unit length of real numbers, it's just -1 plus 1. That's a subgroup. Similarly, the circle, okay, unit circle is a subgroup of the non-zero complex numbers under multiplication. Okay, so these are the easy examples. Any finite dimensional vector space over K is also a topological group. I am only looking at the addition. The scalar multiplication is there. We will study them little later. Similarly, our example, namely I told you about Banach spaces, the set of all bounded functions on X, taking values in either R or C. Okay, that was a Banach algebra, right? So there the addition will be automatically continuous with respect to the topology induced by the norm. The norm is supremum norm. Okay. One of the most interesting case of all these topological groups occur inside the matrices of n cross and matrices. Addition there already makes it a topological group. Okay. Even the multiplication, just like in the case of complex numbers and real numbers, of course, you have to throw away the zero matrix, right? Not only zero matrix you have to throw away, this time you have to throw away a lot more, namely all matrices of determinant not equal to 0. Determinant equal to 0, you have to throw away. So in other words, you have to take only invertible n cross n matrices, invertibility with respect to multiplication. So that will form a group, and the group laws are continuous. How do you take inverse of an invertible matrix, n cross n matrix? Each entry will be a polynomial, namely the ijth cofactor divided by the determinant. So it is polynomial divided by polynomial, but the denominator is non-zero. Therefore, they are continuous. Okay. So GLNK forms a group, and the group laws are continuous with respect to what? With respect to the Euclidean topology there. GLNK is an open subset of all K, n cross n I am writing, which I have told you earlier. Namely, you write it as, n cross n vector. You think of that as n cross n vector. So that way you get a Euclidean topology on that. Okay. Similarly, you can look at ON, which is defined as all those matrices, real matrices, okay, such that A transpose is identity. If you take complex matrices and then take A star, namely conjugate transpose, right, A star, that's equal to identity, that will be called the unitary group. So verification that they are groups is easier. It is linear algebra, matrix theory. The only missing thing was why the group multiplications are continuous. You can separately verify that A comma B going to AB is continuous by looking at the matrix entries of this product. They are all polynomials. Then you have to look at whenever this is invertible, then how to write the inverse? So for writing the inverse, you have the Kramer's rule, which says take the adjoint matrix, which is again each entry is a polynomial in the original one. Then each entry you have to divide by the determinant of the given polynomial, given matrix. So that's also another polynomial, right? So that is the whole idea of this GLNC, okay, and GLNK in general. GLNR and GLNC are special cases. They have various subgroups. I have denoted only two of them here, ON and SUN here. Then you can take groups with determinant 1 also here. They will also form another subgroup, smaller subgroup, and so on. So these groups and many other groups are, central to a lot of mathematics. And there are theories here. A small aspect of this you can call them as matrix groups, which will lead to what are called as later on a deep theory, very beautiful theory, Lie groups, which we will not be able to do. Okay. So let us stop here and take up these discussions next time. Okay. Thank you.